In this video, I'm going to explain to you a little bit about JFET biasing. And we see here, we have a JFET device. This is an N-channel JFET device. We've got our three terminals, the gate, source, and drain. And the voltage between the gate and the source is going to control the size of this depletion layer here. It's going to make it either bigger or smaller, which is going to control the size of the channel that we have between the drain and the source. And then the voltage between the drain and the source is also going to be controlling how much current is going between the drain and the source to a certain extent. And we'll see what that extent is in a few minutes. And over here, this is sort of a refresher of the relationships between the gate source voltage and the drain current, as well as the relationship between the drain source voltage and the drain current. Now maybe we should look at this particular picture first. So we've got several different curves here, and these different curves correspond to different values of the gate source voltage. But if we pick any particular curve and we consider increasing and changing the value of the drain source voltage, so let's look at this one. This one's the most extreme one. So as we increase the drain source voltage, the drain current increases in almost a linear manner, sort of linear up to around this point or so. And so as you increase the drain source voltage, the drain source current is going to be increasing up to a maximum. And then once we reach that maximum, increases in drain source voltage result in very little increases in the drain source current. And we get similar shaped curves, but with a different maximum current for the different values of the gate source voltage. And what you can see is we've got two different regions determined by the drain source voltage. We have a linear region, where the relationship between the drain source voltage and the drain current is approximately linear. And then we have a saturation region where for increases in the drain source voltage we have very little change in the drain source current. And it's at the saturation region that we're going to focus on for this video. And it's in the saturation region that we want to be if we're going to use this JFET as an amplifier. And the relationship between this particular graph here and this particular graph here is that this graph represents the saturation region. So this blue line here represents the saturation region. So as long as our drain source voltage is big enough to push us into the saturation region, this is the relationship that we'll have between the gate source voltage and the drain current. Right, we have some pinch-off voltage, so any voltage below this pinch-off voltage is going to make the depletion layer so big that we actually close the channel and we have no current going. And then as we increase the gate source voltage, we increase more and more and more, our drain current increases more and more and more until we get to some maximum. And this maximum occurs when that gate source voltage starts to become forward biased, and we no longer have this depletion region, and the behavior is no longer we no longer have our circuit in the saturation region, or our JFET in the saturation region. So our saturation region actually only exists between these 2 points, and the relationship between those two values, the gate source voltage and the drain source current, is called Shockley's equation. And Shockley's equation looks like this. The drain current, or we call IDS in the graph there, is equal to IDSS times 1 minus the gate source voltage over VGS off all squared, and that VGS off is called VP in the graph here. So we've got VGS off as our VP there. This point here is IDSS. This is the maximum that your drain current can reach. And IDSS stands for the drain source current at saturation. So here's an example showing Shockley's equation at work here. I've rewritten Shockley's equation, and I've got this particular transistor that has these characteristics. And so with any particular transistor, you could JFET, you could look up these characteristics, the VGS off or the VP and the IDSS, and they're going to be characteristics of the transistor. So minus 4 volts VGS off and 8 milliamps for IDSS. And we're going to plot the characteristics, the transfer curve, the transistor characteristic curve for this particular transistor. So we can plug these numbers in. We can plug some numbers into the equation and come up with a graph So let's first just create a table here. So VGS and ID. So if we have a VGS of 0 volts, we plug 0 volts into our equation here. We'll have 1 minus 0 squared, which is just equal to 1. So at 0 volts, ID is equal to IDSS. We can plug the actual numbers in. So we end up with IDSS, which is 8 milliamps. So at 0 volts, we're going to have a point right there. 0 volts, 8 milliamps. At the other extreme, we could have VGS equal to minus 4 volts. So minus 4 volts, we plug the number in, minus 4 over VGS off, which is also minus 4. So that'll just be 1. 1 minus 1 is 0. 0 squared is 0. 0 times IDS is 0. So we've got ID of 0 milliamps. And we can plot that on our graph here. VGS of minus 4 gives us an ID of 0. What about some points in between? If we choose minus 2 volts here, plug in minus 2 volts. Minus 2 over minus 4 is 1/2. 1 minus 1/2 is 1/2. Squared is a quarter, so this is going to be IDSS over 4. So 8 milliamps over 4 gives us 2 milliamps. And that point on the graph is minus 2 volts, minus 2 milliamps. And the one final point in here, let's use minus 1.2. Minus 1.2 volts, we plug minus 1.2 volts into the equation here, and we end up with 4 milliamps. And so a minus 1.2 and 4, we get another point. And we can interpolate between these lines. We get a curve looking something like that. Maybe a little bit more curved, but you get the idea. Now why do I have this other graph over here? Well, this is my graph of the relationship between the drain source voltage and the drain current. And I just wanted to reiterate the fact that this is for saturation region only. So a VP, a VGS off, doesn't matter what the drain source voltage is, we're going to have 0 current. So that's for VGS equals minus 4 volts. For VGS of minus 2 volts, the second curve, I'm going to redo these in red here. So at minus 2 volts, we're going to have a saturation at some value, I guess ID of 2 milliamps. We're going to have saturation at about here, and before that will be in the linear region. So we're going to have a curve looking like that. And this is for VGS is equal to minus 2 volts. And for VGS is equal to minus 1.2 volts, our ID is going to be at this point here. So we're going to reach saturation at 4 milliamps. And before that, we're in the linear region. So I'll have a curve looking something like that. And that's at the VGS equals minus 1.2 volts. And then finally, at VGS equals 0, we're going to have a drain current at a maximum at IDSS. ID will be equal to IDSS. And before the active region, we're in the linear region. So we have a curve something like that. That's VGS equals 0 volts. And our ID is at IDSS of 8 milliamps. And so just to reiterate that this curve here corresponds to the saturation region for the VDS versus ID graph. Now, as an exercise, see if you can figure out what the transfer curve is going to look like for this JFET that has these characteristics, an IDSS of 12 milliamps and a VGS off of minus 6 volts. If you pause your video right now and take a second to try to figure out what that transfer curve is going to look like. Well, the first thing you're going to want to do is find a few points, and so 4 points is probably good enough. You want them at the extremes, so at saturation, at the maximum ID, and at the minimum ID or pinch off, and then a couple points in between, and good points would be 0.3 VP and 0.5 VP. And now you've got 4 points, and you can sort of sketch the curve based on those 4 points, and hopefully you came up with something that looks like this. My 2 extreme points, and then a couple points in between, and there's all the points sketched in between. Now what the heck are we going to use all this information for? So we've got Shockley's equation and we can sketch a graph of Shockley's equation. Well, the reason that we want to do this is we want to find the biasing point for a JFET circuit. Just like what we did with the transistor, with the BJT circuits, find the DC operating point or create a DC operating point so that our amplifier circuit, or so that our circuit can operate the way that we want to operate it, the way that we want it to operate. And usually that's going to be as a Class A amplifier. So, here's a simple example of a 2 power supply biasing circuit for a JFET. Alright, we've got our N-channel JFET here, connected to a biasing voltage, biasing power supply here, connected to ground and also to the source, and then up here in the drain we're connected to a 16 volt source through a 2 kilo ohm resistor. And for this particular transistor, this particular JFET, IDSS is 10 milliamps, and VP or VGS off is equal to minus 8 volts. And what we want to find is for this circuit, I guess I should 1 mega ohm here. For this particular circuit, we want to find the DC operating point. That includes the gate source voltage, it includes the drain current, and it includes the drain source voltage. So, to start off with, in a JFET, the gate current is going to be pretty much 0 amps. And since we've got 0 amps that is flowing into the gate here, the voltage between the gate and the source is only going to depend on this power supply here. We got 2 volts. So the gate is going to be 2 volts lower in voltage than the source. So VGS is equal to minus 2 volts. Second thing, well, we actually have enough information here to figure out what the drain current is. We can use Shockley's equation. ID is equal to IDSS times 1 minus VGS minus 2 volts over VGS off minus 8 volts, and then that's all squared. Plug those numbers into our calculator and we get 5.625 milliamps. We have the gate source voltage, we have the drain current, so we actually know what point on the transfer curve we would be. But the final thing that we want to figure out is the VDS. So we can use Kirchoff's voltage laws to figure out the drain voltage and the source and then the VDS. So the drain voltage is the voltage at this point with respect to ground. So we know the voltage here, we've got 16 volts from the source. We're going to have some amount of drop across the 2 kilo ohm resistor, and that drop is going to be just based on Ohm's law, 0.01 amps times 2 kilo ohms, and that all works out to 4.75 volts. VDS, or I guess VS, well, the source is connected straight to ground, VS is equal to 0 volts. Therefore, VDS is equal to 4.75 minus 0, or 4.75 volts. So we've got the operating point. We've figured out where on the transfer curve we are and what our drain source voltage is. But this particular circuit, not so great. Why? Well, because we have 2 voltage sources. Not so easy to design with 2 voltage sources. It's going to make your circuit, the actual physical circuit, much bigger, and that's not something that you will usually want. Now, here's a little bit better type of biasing circuit. It's called self-bias. Self-bias JFET circuit. And it looks something like this. We've got, I'll show the V in here even though we're not dealing with the AC part, we're only trying to figure out the DC part. V in applied to our gate for this N-channel JFET, and at the gate we're biasing the gate by using a resistor between the gate and the source. We've got a resistor between the source and ground, and we also have a resistor up here in the drain. And for this particular transistor, we've got the characteristics of it: 8 milliamps for the IDSS and minus 6 volts for the VP, the V pinch off. Now I'm going to throw some numbers in here just so we can do some calculations with numbers. Let's say we've got a 20 volt DC source 3.3 kilo ohms here in the drain, 1 kilo ohm here at the source, and 1 mega ohm over here at the gate. So now we're going to have to use some algebra as well as some Kirchoff's voltage laws and Ohm's laws to figure out the relationship between, or the values of the drain current, the gate source voltage, and the drain source voltage, so we know what the operating point of this circuit is. So some things we know about this circuit. We know that the current into the gate is equal to 0 amps. There's no current going into there. Therefore, the voltage at the gate is 0 volts. We've got this 1 mega ohm resistor connected here to ground, so our gate, we know our gate's at 0 volts. We also know that the source voltage, the voltage at this point, is going to be equal to whatever current is going through this 1 kilo ohm resistor times the resistance. Source voltage is equal to 1000 ID. This is just Ohm's law, the voltage drop across this particular resistor. And so, let me number these things. 2 things we know. The third thing we can figure out from here, gate source voltage. The gate source voltage is equal to the gate voltage, which is 0 volts, minus the source voltage, which is minus 1000 ID. So we've got one equation set up here. The other thing we know about this overall circuit that we can relate the gate source voltage to the drain current is Shockley's equation. This is just the thing that holds true for JFETs. So we know that the drain current is equal to the drain source current at saturation, or IDSS, is 8 milliamps, times 1 minus VGS over VP, which is minus 6, all squared. So I've got 2 equations here. Let's call this equation A and equation B. And I've got 2 unknowns. We've got VGS we don't know, and we've got ID we don't know. ID we don't know, and VGS we don't know. If we have 2 equations and 2 unknowns, we can solve for both of those unknowns. So it's a simple enough concept, except it's just going to take several steps of algebra. So hopefully you remember all your algebra simplification and substitution, equation substitution, and even the quadratic equation. So I'll just go through this really quickly. So what we do, we've got VGS is equal to basically minus 1000 ID. So we'll plug that number, which is VGS, into here, and then we just solve for ID. So we get ID is equal to 0.008 times 1 minus negative 1000 VD, sorry, negative 1000 ID over negative 6, all squared. And we multiply this all out, we get 0.008 times 1 minus 166.7 ID minus 166.7 ID plus 27,777 ID squared. And we put this in a form that we can solve, and we get 222.22 ID squared minus 3.67 ID plus 0.008 is equal to 0. Now this is in a form where we can use the quadratic equation to solve. And if you remember, the quadratic equation is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a, where in this case, let me draw some arrows here, b is this number here, a is this number here, and c is this number here, and x, well, that's ID. And now we have to solve for that, and what we end up with, because the quadratic equation actually gives you two answers, we get ID is equal to 13.9 milliamps and 2.58 milliamps. And we have to pick which one of these is the correct one. And if we were to, remember, if we plot out the transfer curve, it's going to look something like this. That's not a very good line. Maybe if I draw it in red it'll look better, or I'll be able to draw it better. No, apparently not. One more try. Okay, that's the best I can do there. And in this case, IDSS, this is 0.008 milliamps. So this is the maximum that the ID can be. And so if we're looking at the solutions we have for ID, we have a 13.9 milliamps. Well, that's going to be somewhere, if we were able to carry this on, that's going to be somewhere up here. Now it's going to be a correct location on the entire parabola that we could draw here, because remember also this way we reach 0 and we'd carry on over on this side, except that it's not a valid value for a JFET. So it must be the valid answer must be this 2.58 milliamps, which actually falls on the transfer curve. So somewhere around this point. So if we've got an ID, so we're going to use ID of 2.58 milliamps as our correct answer. Now the last piece of information that we need is VDS. What is VDS? Well, VDS, let's go back up to the graph here. The voltage between this point and this point. Well, again, we can use Kirchoff's voltage law. We're going to have 20 volts minus the voltage drop across this resistor minus VDS minus the voltage drop across this resistor brings us to 0. So what does that equation look like? IDS equals 20 volts from the source minus the voltage drop across a 3 kilo ohm resistor minus, actually, that's not quite right. I'm going to say VDS equals, here's my equation. It's not VDS equals, but just the Kirchoff's voltage law for that particular loop. 20 volts minus the voltage drop across the 3K resistor minus the voltage between the drain and the source minus the voltage drop across the 1 kilo ohm resistor. That brings us down to 0 volts. So rearranging this equation and solving for VDS, we get 8.91 volts. So we've got our operating conditions here. We've got our ID of 2.58 milliamps. We've got our VGS. So we didn't even plug the numbers in for VGS, did we? VGS is minus 1000 ID. So that equals 2.58 volts. And we have our VDS of 8.91 volts. Well, of course, VGS, that's a negative voltage, so negative 2.58 volts. So in this really rough sketch that I've got here of the transfer curve, this point right there, that's minus 2.58 volts and 2.58 milliamps. And then on the graph of ID and VDS, it looks something like this. This is for the VGS equals minus 2.58 volts. Our operating point is at 8.91 volts on there. Now there is another way to solve this circuit approximately, and that's solving it graphically. And it's the same concept that we did in the previous part where we were trying to solve it numerically. And when you're solving it numerically, you're actually, if you've got two graphs, you're finding the intersection point of those two graphs. And if we do it graphically, we just draw out the graphs and inspect for the intersection of those 2 points. So what were our two equations? We had the equation of for Shockley's equation that looked like this. And we had the equation for the gate source voltage. Gate source voltage was minus 1000 ID. So we came up with those two equations previously. And we're going to take these two equations and plot them on this graph here. Now the Shockley's equation, what we can do with Shockley's equation is pick some points for VGS and ID. We'll pick the extremes. We'll start off with when VGS is 0 volts, ID is going to be at its max of 8 milliamps. Look at the other extreme when ID is at 0 milliamps, VGS is at minus 6 volts, and 2 points in between, pick like 0.3 VGS, so 0.3 times 6 is minus 2 volts. And what does that give us for ID? Well, we plug minus 2 volts into Shockley's equation, and we get 0.5 IDSS, which is 4 milliamps. And we use VGS over 2, we use half of VGS, so we pick another point minus 3 volts, which is at a quarter of IDSS. Quarter of 8 is 2 milliamps. So we got 4 points here. We can approximately graph that. We can do a pretty good job of graphing it. Our two extremes, 1 point there, 1 point there, and in between we've got minus 2 and 4. And we also have minus 3 and 2. So let's see how I can do in drawing this out. Oh, I missed. That's okay. The other graph, the other equation that we're trying to graph is VGS equals minus 1000 ID. So this is just a line, so we're only going to need 2 points for it. One of the points we know if we have an ID of 0, our VGS is going to be 0. And the other point, well, we just pick any point really. We could plug in ID of 5 milliamps into here and we get VGS of minus 5 milliamps. So we've got our point at the origin and we've got a point of 5 milliamps and minus 5 volts. I think I said minus 5 milliamps before. I meant minus 5 volts. Let's draw that. Let's do it in blue. Let's do blue. So 1 point there, 1 point there. It's just a straight line. So not very good there. Try again. If I was doing this on paper, I could of course draw a much straighter line. And so the intersection is right here, and that's at about 2.66 volts and about 2.5 milliamps. So VGS equals minus 2.6 volts, ID equals 2.5 milliamps. And that's pretty close to what I had when I did it numerically. 2.6 milliamps, 2.6 volts approximately. So graphically I can get a pretty good approximation if I do a good job drawing my graph and I don't have to try to solve, go through all that algebra. So I'm going to hold it up there for now and come back and watch some more videos on JFET biasing. I'll do a few more examples and show you another type of biasing circuit that can be used for biasing a JFET amplifier circuit.